Good morning, everybody, or good afternoon. Welcome to Earth Science. Let's just do a really quick one for the worksheet you're going to do today. I won't make you do this video for too long. Don't worry. I know some of them go long. What we're going to look at is all the data for all the planets, which you can find right here in your Earth Science reference table. So really, there's not a ton new that I want to accomplish today, other than just practicing how to get this data for the planets. I figured, what the heck, why not? Since we're going to have a test coming up soon anyway, let's just remember solar nebula theory for how we got these planets anyway. How did we get this Earth that we're on? And how do stars form? Which would have started with this interstellar cloud of gas and dust. Remember, interstellar, just out there in between stars somewhere. Very low density cloud of gas and dust, and the stuff that would eventually make planets and stars begins to collapse. And as it collapses, remember that accelerates because the more mass is in there, the more gravity will be associated with it. So it pulls in more stuff. So it has more mass. So it pulls in more stuff. So it has more mass. So it pulls in more stuff, so on and so on. So as it contracts, a star forms in the middle when fusion starts. That one vocab word I don't think we're quite there yet. We're going to practice that a little bit more. When fusion starts in the beginning, in the middle, you'll have yourself a star. And as these like rings of debris around the outside eventually clean themselves all up as planets form, as our Earth got bigger and bigger and bigger and it kept on orbiting, all of the chunks that would have still been in that orbit eventually got incorporated into the planet. This would have been, nothing was alive at this point, but this would have been a very violent time to be alive. It was like constant meteorite impacts, an extremely thin atmosphere, no chance of life being on that planet. But here we are today, right? So how did this all happen? So this gives us our star with the nice clean planets orbits, but remember there is that one asteroid belt in there as well too. So with all of that, what do we got to do? I'm not saying that's all we got to do, but I'm saying today's job, all we got to do today is kind of get down how the solar system data chart works. And it is on page 15 of your reference tables, right there with that star one. We can practice in that one as well. Over here, sun, and we've got our 8 planets, and then separately is the moon. So really, sometimes I have people do this. Maybe not a terrible idea. And then the 8 planets, and then all the data. And there's really only one thing that you're going to have to know about the planets. And we'll continue to unpack this one thing, but I'm going to throw it at you today and maybe start to see. I don't know if it's in any of these questions or not, but let's throw it out there. And that is that there's planets 1, 2, 3, and 4 are kind of similar, and planets 5, 6, 7, 8 are kind of similar. And Pluto was always the weirdo. When I first started teaching Earth science back in, I don't know, early 2000s, Pluto was still in the group here. They kicked Pluto out officially because it was more in common with all the other dwarf planets. It was basically bring all of those in and say, now we have all these planets, or kick the one Pluto out and have it be nice and neat and honestly easier for Earth science Earth science students. So what do we notice about these 4? Look at the densities. 5.4, 5.2, 5.5, and 3.9. They're all, compared to these 4, higher. 1.3, 0.7, 1.3, and 1.8. So we got 4 that are more dense and 4 that are less dense. Those fit nice and neatly into groups. Let's also look at their size, their diameter. 4,000, 12,000, 12,000, and 6,000. Yes, I'm rounding. Compared to the last 4, 142,000, 120,000, 51,000, and 49,000. Huge. So we've got 4 that are more dense but smaller, and 4 that are less dense but larger. Now we have fancy names for these. T, J. I really recommend, in fact, if this works right, that might actually just stay there on the document that you open up. Actually, no, it won't. Never mind. Sorry about that. So put that over there. Terrestrial and Jovian is what they stand for, T and J. All right. And I've in past years said, like, just do TJ. TJ. Think of somebody named TJ. If you can do that, boom, boom. Because I think the properties, like, people tend not to get confused on that because you get this reference table on all your tests. There it is. So you can just say, like, oh yeah, I know that they're 4 and 4, and hopefully I also know that the sun and the moon are not planets. So I know that they're 4 and 4. So I got these that have these properties and these that have these properties. Then really the only thing you got to get is TJ, terrestrial Jovian. If you want to write that over here, terrestrial, smaller fonts. Jovian. Jovian. Okay. So outside of that, some of these questions are going to be really just kind of looking and seeing what's going on. Let's just make sure we know what all these columns are, and you can go ahead and do it. Mean distance from sun. How far away is it from the sun? So obviously that increases as you go. That's the order that we put this in. Period of revolution and period of rotation. We're really going to need to be specific on that in the next unit about which one of those is which. So let's, again, start to open the door. If we're not experts in it by the end of today, that's all right. But let's start to open up the door on what those mean. What is a revolution versus what is a rotation? And sometimes, since we live on Earth, people are kind of comfortable with that already. One revolution takes us 365 days. That's a year. One rotation takes us around 24 hours. And we'll talk about why these are off a little bit, the whole leap year thing. So a day, right? So a revolution is a trip all the way around the sun, and a rotation is one spin on your axis. Eccentricity, this one should not get into too deep a detail with it, but we will get very deep in detail with it when we do lab number 9, ellipses. This is a value for how round the orbit is. They're not all, none of them are perfectly circular. They're all a little bit misshapen. How misshapen are they? That's what that number is going to tell us. I wouldn't really panic about it today. The closer it is to 0, the closer it is to a perfect circle. But just note that's what it is. Diameter, you know what a diameter is of the planet? Basically how big it is. Mass with a funny unit where Earth is 1. If we say Earth is 1, what are the masses of the other planets? This one's like 317 Earths, whereas this one's only 0.06 Earths. And density, how dense is the planet itself? All right, what do you think? I think it's very doable. And again, today is just practice. If you're stumped anywhere, let me know, and we'll, yeah, those questions should be pretty straightforward. All right, good job, good luck. The test is coming up next unit soon. Good luck, folks.